And next, the other thing you need when you do these calculations is the charge density. And the charge density at each point is just going to be the magnitude squared of this amplitude, your C1, C2, or C3 in the device, divided by the length associated with that node or that site, um, again weighted by the probability that it's occupied, your Fermi factor that you're injecting from. And so the magnitude of Cj for any arbitrary j in your device is just given by, if you inject from the left, it's given by the first line, and if you inject from the right, it's given by the second line for any arbitrary node j in the device. And to get the total charge density, you need to sum up, what's being injected from both the left and the right. And so what we did was calculate, the superscript sub L is what you're injecting from the left contact. So this would be, the first line is what you're injecting from the left contact. Again, you have your normalization length. You sum over all the k vectors you're injecting from from the left contact. The thing in the bracket, and the magnitude square, that's just your Cj squared, weighted times probability that's occupied. And going through the same steps, converting the sum to an integral over k, converting the integral over k to an integral over e, you get the expression on the bottom line. And that dE dk is going to inverse is like a 1 over velocity, which is going to turn into a gamma. Right? So this dE dk inverse is exactly this. I guess I multiplied through and divided through by a, and that's just 1 over gamma times 1 over a. And so the final expression is, without spin, is this, and then we multiply by 2 and do our same trick with writing gr squared as gr times ga, because that's the way we're going to see it when they actually become matrices. And this way, when you really start working with matrices, if you write it like this, if you notice, every time I've written it out like this, the indices always follow one after another. So it's grj1, gamma 1, 1, ga1j. And if the indices don't follow, then you've probably made a mistake. So keeping track of the indices is just a really good way to make sure you're doing something sensible when you're deriving these, because it's really easy to take a wrong step and go like several days in the wrong direction before you realize, like, oh crap, I got an index wrong somewhere. Okay, so if you inject from the right-hand side, well, it's all the same steps, except now since we're injecting from so the top line is the electron density at any node j, resulting from injecting from the right lead. And your gamma 3,3, that's the gamma from the right lead, and this is basically gr j comma 3 magnitude squared, which tells you, I hit the device, this is how much makes it to node j, and do the same integral. And finally, the electron density, the total electron density, you just sum the contribution from both the left lead and the right lead. And that brings us up to where we were when we stopped last time. Okay, so let me write out the full expression for n sub j, or just, n at node j. So n, let's go back to below. N at node j is equal to 2 over a integral dE over 2 pi I personally just like to keep my 2 pi under the dE because later we'll see it really comes from a Fourier transform. GR, so I'm just summing the two contributions together in the integrand. GR J1, J comma 1, gamma 1, 1, GA 1 comma J plus GR J comma 3, gamma 3, 3, GA 3 comma J times, oh shoot, I wrote down the equilibrium expression, gosh darn it. So this is my equilibrium. I should have written down the non-equilibrium first. And in equilibrium, I got to multiply times there's only one Fermi factor. That's the only difference. Right, in equilibrium, I just have a flat Fermi level, mu, everywhere. So I don't have two different. And in non-equilibrium, I just have to multiply each one by its own Fermi factor. So Nj is 2 over A integral dE over 2 pi. Let me just define these now so I don't have to keep writing them. We'll be using these a lot. They call this a L. That's supposed to be an L. J comma J. And this term is A. R, a script R, J comma J. I'm using a script R. This doesn't mean retarded or advanced. It just means right and left. So I've got A left and A right, which I'm just using it for shorthand. We'll talk about this a lot in a moment. So in non-equilibrium, I've got A left, J comma J, times F from F of E minus mu L plus A right, J comma J, F of E minus mu right. So that's your non-equilibrium. Well, you have to weight them each by their own Fermi factor because one's being injected from the left contact and one's being injected from the right contact. And in equilibrium, you can just add them together, and there's only one Fermi factor, so you just multiply it times the one Fermi factor, F of E minus mu. Okay? Any questions? Now, the equilibrium one is the one of interest at the moment. Because, I mean, you already know the expression for, the electron density in equilibrium in a crystal. You just integrate the density of states times the Fermi factor, right? And if we look at this expression here for our electron density in equilibrium, well, it's something times the Fermi factor that you're integrating. So that something must be the density of states. Okay, so I mean, we know that n, I'll keep my factor of 2 for spin out front, is equal to the integral over energy of the density of states times the Fermi factor. And therefore, just equating the two expressions, I have that the density of states at each site J is equal to 1 over 2 pi A times GR J1 gamma 1 1 GA1J plus GR J3 gamma 33 GA 3J. So, you know, if we were just doing our ideal wire where there's no potential, no, not counting the atomic variation, but no, you know, potential variation across the device, every site's at the same potential, then this is just your 1D density of states. When you have a device and the potential is varying, then it will become a function of position. Slight, you know, and we said this is, so for example, you know, a PN junction in equilibrium, the potential is varying as a function of position. This would give you your density of states at each site, at each position. And in fact, it gives you the density of states in non-equilibrium also. But in non-equilibrium, you can't just, because you have two different Fermi functions now from the two different contacts, then you can't directly use this to calculate the electron density. You have to break it up into the two pieces and multiply by the two separate Fermi factors. And so as part of the homework, you're going to show that this expression here corresponds to exactly the 1D density of states that you get out of the tight binding dispersion. You know, if you start with your tight binding dispersion, what is it? E equals epsilon plus 2t cosine Ka, and calculate the density of states from that expression, you'll see that you get exactly this. And so that's part of the homework. Okay. So we, once we derived that 3x3 matrix and took into account the effect of the leads, all the work was done. Now we're just basically manipulating and giving names to different terms, names that show up over and over again in non-equilibrium green functions theory. So, I mean, the basic derivation is done of starting from Schrodinger's equation, just using algebra to truncate that infinite matrix to get rid of the leads and have this finite matrix in your, quote, device region. And we just use straightforward algebra and the known form of the wave functions in the leads. And, you know, your, quote, self-energies that people talk about just pop out automatically. And we can just, you know, by looking at the form of the matrix, we can see what those self-energies are, these T e to the IKA terms. Give them you know, physical meaning in terms of lifetimes, and show that this matrix gives a correct solution in the device domain. And now the rest is simply manipulating it, giving labels to various terms that are commonly used, and massaging it into the form that is used in non-equilibrium green function theory. But you know, we've done this very direct, step-by-step derivation starting from Schrodinger's equation. I just don't want anyone to lose sight of that. We just started directly from Schrodinger's equation, and are going to end up at all the standard negative equations. Negative meaning non-equilibrium green function. Okay, so the next term that shows up all the time in non-equilibrium green function theory is the spectral function. And the spectral function is basically the density of states, you know, divided by 2 pi over A. So you see this, and it sounds scary, but it's just your density of states within a factor of 2 pi or so. So the spectral function. And the spectral function is always, the variable given for that is always uppercase A. So A, it is a matrix just like your green function. We'll show they're intimately related. So, and it's a function of energy because it is basically your density of states. And that is, you know, in what we've done so far, as in this coherent picture, simply these two terms, your G gamma, GR gamma, GA. So GR J1, gamma 1, 1, GA 1, J plus GR J3, gamma 3, 3. So that's all it is. And it's simply related to the density of states by this factor of 2 pi over A. So A Jj of E divided by 2 pi over A is exactly what we just said was the density of states. And I had just sort of, for convenience, but it goes far deeper than that, said that this term here we were calling A left, JJ, and this term here was A right, JJ. So again, we're going to see that the spectral function, again, in this coherent transport picture, is just built up of the sum of what you inject from the left and what you inject from the right. The only thing that differs is that, you know, if we're doing electron density, we have to multiply each term by the respective Fermi function. Now, since it's the total number of states, then it's always, your Fermi function would be 1 because you're counting every state. You don't care whether it's full or empty. Or you can think of it as F plus 1 minus F. The empty states plus the filled states. That's all the states. All right. So that's our spectral function. And okay, so there it is on the top line with some extra junk. Okay, so this spectral function is, we can write it a far more compact way as A in terms of the matrix now, the full matrix. I just wrote the diagonal elements here. So the full matrix is simply equal to the green function matrix times the gamma matrix times the advanced green function matrix, which is the Hermitian conjugate of the retarded green function matrix. And this is, I believe, always true. This is always true. And, you know, if we look at what that, we write out our green function matrix, this would be our 3 by 3, you know, G11, dot, dot, dot. Our green function matrix, the important thing is our gamma matrix, which only has 2 terms in it, right? times our 3x3 advanced green function matrix, which is just GR dagger. So that's what we're talking about here when I write it formally like this. It's GR gamma GA. And if I write it in terms of indicial notation, the matrix elements of A, M comma N are equal to the sum. Let me just see what they're equal to. So this would be GR M J gamma J comma I GA I comma N. So summing over I, J and I. If I write out what that matrix multiplication is in terms of its indices, that's supposed to be a sum over J and I. J and I. That's supposed to be an I here. J comma I. And the important point is that gamma, there's only two non-zero elements of this gamma Ji in the middle. The only things that are there are gamma 1, 1 and gamma 3, 3. So in all that sum, there's only two terms, which we've already written down. So that's equal to GR M1 gamma 1, 1 GA 1N plus GR M3 gamma 3, 3 GA 3N. Usually you don't need the off-diagonal elements of the spectral function. Usually you just need the diagonal elements, but it's the general form for any M and N, at least when gamma only exists on the corner due to the injection from the leads. And again, when you keep track of the order of your indices, it makes it much easier to write this down. Sort of something you learn the hard way, right? The indices here are first M and last N. So in every term here, the first index has to be M and the last index has to be N. Right? First index in every term has to be M, the last index has to be N. And then everything else in between has to go through sequentially. 1, 1, 1, 1. In this case, it's kind of trivial. All right. So this is the spectral function. So as I wrote down before, once we have this, and we've already said that each one of these terms we give a special name to, our A left, JJ, and our A right. And if they're the off-diagonal elements, you can have an A left, MN, and an A right, MN also. Then, I've written this before, but it's such an important equation and concept, I'm going to write it one more time, because you often see it in the literature too. So the electron density at any site is equal to 2 over A integral, if you have band edge, is at 0. Times the left, people call it the left injected spectral function. Plus the right injected spectral function. All right, So left injected spectral function and the right injected spectral function, and that's the terminology that people use, and this is an equation you'll often see in papers in the literature that are actually using this stuff. So the electron density is the sum of the right and left injected spectral functions weighted by their respective Fermi factors from the leads, where they're coming from. And again, just more notation and sort of manipulation. Nothing really new, we're just manipulating the heck out of these equations. We can define gamma L as simply the matrix where you only have the gamma 1,1 element. Just break this apart into its two pieces, right? And we can define similarly gamma R as simply the matrix, the gamma matrix with only the lower right corner to it. And then you'll often see equations like this in terms of the left and right spectral functions. I was calling it capital L, I'm using a lowercase l. So A left is, people write GR gamma L GA, and A right would equal GR gamma right GA. Again, just the kind of terminology that you see in the literature in terms of the left and right spectral functions. And since gamma is gamma L plus gamma R, just adding them together, then again, it's just another way of seeing it. A is what we wrote down earlier, GR gamma GA, and it just breaks out into its two components, GR gamma L plus gamma R GA, which is what we AL plus AR. All right, just writing in every different way, because this is such a crucial part of many numerical algorithms. It is good to know how to manipulate the spectral function. We'll be manipulating it more when we get into the numerical algorithm part of it. Okay, so far so good. And probably one of the most important equations is the next one. I'm going to write it down, then I'll prove it. That this spectral function that we've been talking about is really the primary definition from which all others can be derived, is equal to I times the retarded green function minus the advanced green function, which is I times GR minus GR dagger, right? Because the advanced green function is just a Hermitian conjugate of the retarded green function. This is one of the fundamental definitions, yikes, in green function theory. It's not just non-equilibrium green functions, but equilibrium green functions, finite temperature green function, zero temperature green function. This is a fundamental definition of the spectral function. So let's see how that, and we also know that it's equal to GR. So we want to prove that those two things are equal to each other. I times GR minus GA is equal to GR gamma GA. All right, these are two fundamental relationships that are used to derive some efficient numerical algorithms when we actually solve this stuff. So let's look at the equations. And the way you do this is going back to what they call the equation of motions for the green function. They call it, it's a funny way to call it, it's just working with the definition. So we have E, okay, I'll put in the identity matrix. E times the identity matrix minus the Hamiltonian in the device region minus sigma r, and for us that's just due to the coupling to the leads, times, remember GR is by definition the inverse of that matrix, right? GR. We define GR as the inverse of E minus H minus sigma. GR is the inverse of E minus H minus sigma, so this must equal, I guess, multiplying a matrix by its inverse, right? So that equals the identity. And now I can take the Hermitian conjugate of this whole equation, and I'm daggering the whole equation, this complex transpose. Whenever you take the transpose, right, you switch the order and you transpose both, and I'll conjugate them also. So I have, well, the dagger of GR is GA, so I have GA times, well, nothing happens to the E in the identity matrix. That's real and it's diagonal, so nothing happens when you take the Hermitian conjugate of that. Well, the Hamiltonian's Hermitian also, so nothing happens when I take the Hermitian conjugate of that. And the only thing that gets conjugated, and I have to change it, the sigma r becomes sigma r dagger. So that's just taking the Hermitian conjugate of that whole equation. Oh, crap. I just lost the top of my pen. Oh, here it is. I hit the chair with it and it popped off. Let's hope it still works. Okay. Okay, so now, well, let me get real formal. 1, 2, from equation 1, really from the definition of the green function, I have GR inverse is equal to EI minus HD minus sigma R, and GA inverse, yikes, and GA inverse which from the definition we could have written down immediately, because GR is just E minus H minus sigma R inverse. But, okay, so that's certainly true. And now what? So now let's go back and look at our the top line up here. So let's look at this expression right here and write it out. So oh no, let's not write that out. Let's write out this one. I times GA inverse minus GR inverse. And so I'll just take the difference of the right-hand sides. I'm just taking the difference of the two right-hand sides. The only thing that stays around are the sigmas. All right, so that's I times sigma R dagger minus sigma R. Or plus, what is it? I got my minus sign. So it's minus sigma R dagger plus sigma R. And if we go back some ways, Um, this is the fundamental definition of gamma. The gamma was related to these sigma r's. If you remember that sigma r has a real part and an imaginary part, I gamma over 2, or minus I gamma over 2, one or the other, plus or minus I gamma over 2. So this is like taking sigma, minus sigma dagger. The real part's going to disappear. And even if it's a matrix, you can break it up into Hermitian and anti-Hermitian part. The gamma comes from the Hermitian part is going to disappear because sigma, if you break it up into Hermitian and then anti-Hermitian components, you're taking the difference of sigma minus sigma dagger. So if there's a Hermitian component, that disappears. What's left is the anti-Hermitian component that gets added together, and then you multiply by I, and that kills off the I. So in our simple case, we had, this was some real part minus I gamma over 2. Sigma r was a real part I'll just write it, a little sigma r, which is the real part, minus I gamma over 2. So negative sigma dagger is just, what is it? Too many minus signs now, I'm getting confused. So sigma dagger is, give me a plus I gamma 2, and then, so this sum here gives me, I guess, minus I gamma. And then you multiply the whole thing by I, and you get gamma, right? If you go back to what our gamma was, what did we have? We had like, on the diagonal, in those corner diagonals, we had E minus HD minus T e to the IKA, I think. So our sigma was T e to the IKA. And if you write that in terms of cosine and sine, the imaginary part is plus or minus a sine Ka. Yeah. Which was a velocity, which is a gamma. Okay. So here we have this, and now what are we going to do with it? What do we do? I see. So now we just take this whole equation. Let me see if I can move it to the next page. Okay, so we take the equation in red, and we multiply it on the left by g sub r. So I'm going to multiply the whole equation on the left by g sub r, and the whole equation on the right by g sub a on both sides over here. So the right-hand side is obviously gr gamma ga. Right? And the left-hand side, if I do this, I get I times, well, the gr, multiplying through by the gr from the left is going to kill off this term, just give me an identity, and then when I multiply through by ga, ga just goes in here. So this ends up as, what's it end up, gr minus GA. Just multiplying through. From GR on the left and GA on the right. And so that's equal to GR gamma GA. The right-hand side is trivial. Which is all equal to our spectral function. Right, do you see what I did on the left? Just multiplied that term in parentheses by GR on the left and GA on the right. And it works whether they're matrices or scalars. Okay, so this is a crucial set of relationships right here. Two different forms for the spectral function. The one on the left is probably the most fundamental definition, but I think the middle term is also completely general. All right. And if you only want the diagonal elements of the spectral function, which is what you need to get the electron density, then A JJ is just equal to I times GRJJ minus GR star JJ, right? Because GA is GR dagger, and we're looking at the diagonal elements. And that's equal to -2 imaginary GR JJ. So this is another expression that you see all the time. The spectral function is just given by -2 imaginary diagonal elements of the spectral function, -2 imaginary diagonal element of the green function. And so what that means is that, you know, once you again, I keep saying, once you calculate that green function, the inverse of that matrix, you have pretty much everything you need. I mean, to get the green function, you needed those self-energies to begin with. From the self-energies, you have your gammas, and it's the gammas and the green functions that give you everything. But from your green function, you get the spectral function. And again, that's going to help us when we talk about numerical stuff. So, you know, again, if you just were interested in, well, we've already said, you know, the spectral function is you know, like 2 pi a times the density of states. So your density of states is given by, you know, -2 imaginary. Or, okay, your density of states, if you want your density of states, d of e. What did we say? I divide the spectral function by 2 pi over a, so that's equal to -1 over pi, and you see this expression a lot, imaginary g. And usually this is what you see because they're not worried about the length, but if you're on a lattice and you want to give it the right units, you put in the length of your associated with that site. And just like we had that our advanced green function is just that's supposed to be a dagger, Hermitian conjugate of the retarded green function. In the same way, we can define an advanced self-energy that's just the Hermitian conjugate of the retarded self-energy, which is the one we derive in the corner elements of our matrix. And then, just like the spectral function is equal to I times GR minus GA, this gamma, which really has no name, is equal to I times sigma R minus sigma A. And if you look at these definitions, since sigma A is sigma R dagger and GA is GR dagger, if you take the dagger of this, then it's clear that A equals A dagger and gamma equals gamma dagger. In other words, they are Hermitian. These two things are Hermitian. Right? Because if I take the dagger of A, I end up with GA minus GR times negative I, which is exactly what I started with. Same with the gamma. If I take the dagger of gamma, I get sigma A minus sigma R times negative I, which is the same thing. Okay. So we've just been taking a lot of terms that we had from our three corner elements of our matrix and giving them special names and showing the relationships between them. Now, let's talk about when people talk about non-equilibrium green functions, there's really a special function that's sort of the target of all the calculations. And Superdata, I don't know if he started it, calls him G sub n and G sub p. In the more traditional literature, they were called G less than and G greater than. But from these things are what give you the electron density and the hole density. And we already have expressions for the electron density and the hole density. So it's just a matter of manipulating what we've already done to get expressions for these. They're really not green functions, they're correlation functions. So let's just write down again our expression for the electron density. And so what we're looking at now are these, people call them green functions, but they're really not. But if we're thinking in terms of 3x3 matrices, they would be 3x3 matrices. The diagonal elements will give you the electron density and the hole density for these things. So let's look at our expression for the electron density again. So we've got that our electron density at site J is equal to 2 over A integral over energy and I'm just rearranging the order of which we wrote stuff before. So this is GR J1 and I'm grouping the gamma and the Fermi factor together. So that's the component that's injected from the left contact. I guess that should be a mu sub left from the left contact. Right, so that's the component. And all I've done is I've moved the F inside the brackets, grouped it with the gamma, plus the part that's injected from the right contact, which is GRJ3, gamma 33, F of E minus mu right from the right contact, GA 3J. Okay, so this is exactly the same expression we wrote down before. I've just grouped the gammas and the F's together. Is all I've done. It's the only difference. And I'm going to these things I have grouped together. I'm just going to give a name to them. So these things I've grouped together. The first one, just like I had a G sub n, I'm calling this a sigma sub n 1, 1, which I'm defining as gamma 1, 1 times F of the left contact. And similarly for the other term, call this gamma n 33, this gamma 33 F of the right contact. Right, I just group them together and then I give them a name, and similarly I can define, now that I have that, just like I've done before, my 3x3 matrix or n by n matrix. Sigma n is just a matrix where I have sigma 1, 1, and sigma 3, 3, and nothing else. Okay. Just like we did for sigma r and gamma and all the others. And so now I'm going to write down G sub n as equal to GR sigma n GA. And if we go through this same, this is a multiplication of 3x3 matrices. If we go through the same exercise that we did with the gamma, there's only two non-zero terms, the sigma 1, 1 and the sigma 3, 3. I get exactly what I had in that integrand, or in general, I get Gn Ij is equal to GR I1 gamma 1, 1 F of E minus mu left GA 1J. So that's from the left, and the part from the right, GR I3 gamma 3, 3 F E minus mu right times G A 3 J. So those would be the Ij elements of this, really a correlation function. Gn, and the diagonal elements The diagonal elements are just exactly what we've written down that we need for the electron density. So the electron, in terms of this new matrix or function that we've just defined, in terms of this guy, your electron density, Nj, is equal to 2 over A integral dE over 2 pi G sub n, or G superscript n, the diagonal elements of this. And this is as simple as that. So this is our, we haven't done anything, we just defined this new, if you're speaking loosely, you can call it a green function. This new green function, and now we can write the electron density in this really compact way. Just the diagonal elements of this 3 by 3 or n by n matrix. Because now we incorporated the Fermi factors. We incorporated the Fermi factors directly into this gamma matrix. Before that, on the corner, we just had gamma 1, 1 and gamma 3, 3. And now we multiply each one by their respective Fermi factors. We call it sigma n. And find this new green function. G superscript n. We can do exactly the same thing for if we simply replace the Fermi factors F with 1 minus F, we get the whole density. So everywhere we had an F, we replace it with 1 minus F, and that's going to give you your whole density. That's usually referred to as P. And we can define ourselves the corresponding, before we had sigma n, now we can just define a sigma p, where it has the two same corner elements, sigma p 1, 1. It's just gamma 1, 1 times 1 minus f of E minus mu L, and gamma, or sigma p 3, 3 is gamma 3, 3 times 1 minus f of E minus mu R. And with those two terms, we define our full 3 by 3 matrix. It's just these two corner elements. We have our new, just going, the only thing we've done is replace F by 1 minus F. We have, instead of G sub G and GP, which gives you the whole density everywhere. That's just GR sigma P GA. And so the whole density, Pj, at any site is just 2 over A integral dE over 2 pi times this, the diagonal elements of this G, P, J, comma J as a function of energy. It becomes that simple. And if you write it all out, it looks just like our expression for the electron density, except wherever you had an F, you now have a 1 minus F. So if we were to write this out, let me just put it on the next page just so it's clear. So to not get too long, that would be dE over 2 pi times our A left J of E times 1 minus F of E minus mu L plus A from the right, J of E times 1 minus F of E minus mu from the right. I'm missing a bracket, one more bracket maybe. All right, so it looks just like the equation for the electron density, except you replace, wherever you had an F, you replace it with 1 minus F, and you get the whole density, which is pretty much everything you need for most device simulations. So now we have an expression for the current, we have an expression for the electron density, we have an expression for the whole density calculated completely quantum mechanically. And then you can feed that into Poisson's equation, do something self-consistent, feed your potential back into your Hamiltonian and iterate the convergence. And if we look at these definitions of, I guess the next fundamental definition, if we look at the way we define sigma n and sigma p, then gamma, here's another fundamental relationship, always true, and you can take this as a definition, is sigma n plus sigma p, and that's equal to, how did we define it before? I times sigma r minus sigma a. If you look at the way we do, sigma n was just, we had our gamma times f, sigma p is our gamma times 1 minus f, you add them together, the f's go away, and you just get gamma. And similarly, if you think of what Gn and Gp give you, if you think kind of physically, I know we're only talking about the diagonal elements gives you the electron density and the whole density, but at any given energy, if you add up the electron density, and this is not the way you think about it in your normal semiconductor device course, where you only talk about holes. I'm talking about take the conduction band, and at a given energy, you calculate the electron density, and at the same energy, you calculate the whole density, which just means 1 minus F. You add them together, well, you've just calculated the density of filled states plus the density of empty states. That's the total density of states, right? So the sum of these two, Gn plus Gp, is your spectral function, which is also I times gr minus ga, which is also gr gamma ga. So, which is also, what else can we write? It's also
guess. Yeah, I guess I got it all down here, all the relationships. I guess I really didn't. I just sort of wrote it down. What I have written down in the notes, just to prove this, is that Gn is Gr, sigma n Ga, and Gp is Gr sigma p Ga. So that's, Gr times sigma n plus sigma p Ga, the sum of those two, right? Because Gn is just Gr sigma n Ga, Gp is Gr sigma p Ga, and by the way we defined it, the sum of those two is just got to be gamma, which is just Gr gamma Ga. In equilibrium, which for us that just means that you only have a single Fermi level, same everywhere. Then you have these very nice relationships that sigma n of E is just equal to F, the Fermi function, times gamma of E. And they all have this parallel, both the sigmas and the green functions have a very sort of parallel relationship. So sigma p of E is just 1 minus F. The Gn, which gives you the electron density, is just equal to F times the spectral function. And similarly, Gp of E, which gives you the whole density, is simply 1 minus F times the spectral function. Okay, so these are equilibrium relationships, which, so again, probably the most important thing, which is, once you understand that you can get the density of states from the green function, then it's clear that in equilibrium, once you calculate the Green's function, which gives you the spectral function, then you immediately have the electron and hole density, because you know the Fermi level mu. So in equilibrium, all you need is the retarded Green function, and you've got your electron density and your hole density. And that's pretty much all there is to it, because you know the current is 0 because you're in equilibrium. And these relationships here are we've done these derivations in a very limited way, right? Starting from this coherent transport problem. But these relationships are true in general, whether there's incoherent scattering or whatever. So these are equilibrium relationships that are always true. And now let me write down, often you see these equations formulated in terms of what they refer to as the equations of motion for the green functions. We've already written down two of them, and that's for the retarded and advanced green function. And simply from the definition, you know that GR was E minus H minus sigma inverse, then E, and I'll be explicit, times the identity, minus H D minus sigma R, which by definition is GR inverse, right? And that was how we defined it. Times GR, which is by definition the inverse of the thing on the left, has got to equal the identity, because that's just the way we define the retarded green function. It's the inverse of that thing in the brackets. But when you write it like that, people call that the equation of motion for the green function. And similarly, E times I minus the Hamiltonian in the device region minus, well, since GA is GR dagger, I mean, and sigma R dagger is sigma A, I'll just write this like this, GA equals I. And, you know, since this one is, since I'm just writing an equation for, you know, something times this inverse, right? That's all this is. And so, right, inverse is always commute. So I could equally write GA on the left or GR on the left, because inverse is always commute, right? So A times A inverse is equal to A inverse times A is equal to the identity, right? So I can also, just to be clear, write this. It's also true that GR times E minus H D minus sigma R is also the identity, because they're inverses of each other. Doesn't matter whether I write A inverse or A inverse A. And same for the second equation too. I can reverse the order of that. And now, so that we've already seen, and that seems kind of obvious because that's the way we define what the green function was, the inverse of that matrix. The equation of motion for Gn and Gp is now, I'm going to quit writing the identity, just it's implied E times the identity minus H sub D minus sigma R acting on G sub n is equal to sigma n and so when it's written like that, that's called the equation of motion for G sub n. So if we just multiply through by, right, I mean, this thing on the left is GR inverse. So we multiply through by GR, and we have exactly what we wrote for the equation for Gn. Gn is GR times sigma n times GA. I just moved that's, you know, right, this thing is GR inverse, right? So if I multiply through the whole equation by GR, I just get that Gn is what we wrote down. These are two entirely equivalent equations, GR, sigma n, GA. Entirely equivalent. But if you write it like I did in the first line, you call that the equation of motion for G sub n. And similarly for G sub p, E minus H sub D minus sigma R acting on G sub P is equal to sigma P. GA. So again, GP is GR sigma P, GA. So these are the two new equations. And there's sort of the fundamental equations because really everything you calculate comes out of Gn and Gp. They're sort of the fundamental things you're after. Non-equilibrium green function theory. And because they don't have an identity matrix on the right-hand side, they're not green functions. Right? A green function equation looks like this. Something hitting your green function gives you the identity matrix, which is like a delta function if you're working in continuum representation. Right? These things, because they have this right, and what this right-hand side is what people call your source term. This is your source term on the right-hand side. Sigma n is F times gamma. So it's what's coming in from the contacts. So you have, this is the most obvious way, which we've seen over and over again. So Gn is what's coming in from the contacts, and then how it propagates from the contacts into whatever position in the device you're interested in. And how it propagates is if you think of combining GR and GA as just GR magnitude squared, that's how it propagates from your left lead or your right lead into any site in your device. So it's just a matter of multiplying through. So this is really, another way I could write this is GR inverse Gn equals sigma n GA, right? That's the exact same equation, much more compact form. Because E minus H minus sigma is GR inverse. And same with this one down here. GR inverse GP is sigma PGA. Exact same equation, just very compact. Okay, so those are the equations of motion for our two green functions and two correlation functions. The equations of motion for GR, GA, GN, and